Hi again, and welcome to part 2 of this video on integrated broadband analog delay circuits. In part 1 we took a look at the motivation and background for our work in this area. In this next part of the presentation I'd like to get into some integrated circuit implementation techniques for continuous time analog delays. Now delay circuits can be categorized as shown on this slide. Remember that for this presentation we're focused primarily on continuous time delay circuits. And those can be categorized as arising from passive components only, or those that make use of active elements. Passive analog delay circuits generally have lower power consumption, introduce less noise, can be very linear, and have higher bandwidth than circuits that make use of active elements, precisely because they avoid the power consuming and noise inducing and nonlinear active devices. That is, transistors. On the other hand, depending on your delay targets, passive analog delays can be impractically large for integrated circuit implementation. On the other hand, if we allow ourselves some active components, we can have much smaller area, and we can also avoid the losses associated with passive circuit elements, so our active delay circuits can have a gain of 1 or even higher than 1 if we so desire. Now, within active delay circuits, I think it's useful to further distinguish between those that make use of feedback amplifiers and those only making use of open loop amplifiers. Now, within those two categories, we're going to be somewhat more interested in those that make use only of open loop amplifiers, because the use of feedback generally requires some trade-offs that limit the bandwidth of operation, and here we're interested in very broadband analog delay circuits. The main drawback of open loop delay circuits that's going to trouble us is that the open loop amplifiers tend to be more nonlinear than those employing feedback. So we'll talk about strategies for mitigating that as well. So let's first focus on continuous time analog delay circuits that use only passive circuit elements. So just a reminder that analog delay circuits using only passive components offer a variety of benefits, especially for broadband analog delay circuit implementation. But their main drawback is that they can consume very large area in an integrated circuit, especially if we're targeting long delay times. The good news is that technology trends and application trends have meant that we're now pushing towards higher speed applications. And as a result, at these higher speeds, it's actually shorter delay times that are of more interest. And as a result, passive delay circuits are actually becoming of greater interest recently in the R&D community. So within passive delay circuits, we can further categorize implementations as those relying on lumped elements, usually lumped LC elements, either in a ladder configuration or a lattice configuration, as shown here, and those using straight up transmission lines integrated on chip to realize a passive delay. So we'll first talk about the lumped element passive delay circuits. These, in any configuration, form a low pass network with a limited bandwidth over which they offer constant delay. Moreover, their area is fairly large, especially when we require long delay times, mostly because of the need for the inductors on chip. On the other hand, transmission lines can provide a wider bandwidth of constant delay, or approximately constant delay, but they require an area that's even larger, typically, than what we see for the lumped LC elements. And one common place where broadband passive delay circuits are used is to distribute a load capacitance along a delay line. So imagine you've got a RC network such as the one shown here. A source is driving a capacitive load. The problem that often arises is the source and or load resistances combine with the load capacitance to form a left half plane pole that limits the bandwidth of the response from VI to VO in this case. Now it's well understood that if the capacitance is of a type that can be split into many smaller parallel capacitances, as shown here on the right, and we can introduce inductance between those now smaller capacitance values. We can change the network from a single pole low pass RC network to an LC ladder network with a much higher bandwidth, whereas the bandwidth on the left is related to the product 1 over RC. Instead, on the right, the bandwidth is related to 1 over root LC. So we can extend the bandwidth quite high by appropriately choosing the values of these inductances. This premise is used all the time in circuits like distributed amplifiers, in ESDT coils, and elsewhere. It's a principle that's been established for decades and used already with great success. But what's interesting is that once you do this, you're actually forming delayed versions of the input waveform VI at various points along this LC ladder, and that can be taken advantage of to perform other types of analog signal processing. And this paper here 20 years ago recognized that this idea could be very useful for distributing the capacitance associated with ESD protection circuits and increasing the bandwidth limitation that arises at input or output pads as a result. So the idea presented in this paper was that the ESD capacitances could be split by taking the diode and breaking it up into many smaller parallel diodes and separating them by inductors, on-chip inductors, whose values are chosen in general to ensure good impedance matching. But again, having done so, you can see delayed versions of the signal at various points along this LC ladder, sometimes referred to as an artificial transmission line, since the differential equations that govern voltage and current phasors along this LC ladder look quite similar to those that relate the voltage and current phasors along a transmission line. So with these delayed versions of the signal, you kind of have delay circuits for free, even though the main reason for doing this was to increase the bandwidth associated with this node. You can essentially take weighted sums of various voltage waveforms along this ladder and implement a finite impulse response FIR filter here. And that's exactly what was done in this paper from 2015. Similar technique was used in this paper from ISSCC 2021. The values shown here are taken from the first paper, and you'll see that they essentially took an ESD capacitance and the associated pad capacitance and separated them with inductor values that had values of approximately 400 picohenries. So you can see these are not tiny circuits, but they're practical for on-chip integration. The capacitances represented a total capacitance of less than a picofarad, and they then took a weighted sum of the voltages at these two nodes, realizing a two-tap FIR filter with a tap spacing of about 20 picoseconds. That's the delay between this node and this node in this LC ladder. So having used a trick like this to distribute the capacitances on the input side of the filter and alleviate any bandwidth limitations there, we may get a secondary bandwidth limitation now arising at this output summing node because many amplifiers are coming together all into one node. But it's been long known, again, here's the original reference I found from 1971, in fact, that these output capacitances could also be distributed using a structure such as the one shown here in the bottom right. So here we've got an LC ladder on the input side, and we've got a 3-tap filter, so we're tapping off 3 delayed versions of the input here and summing them together in an output delay line, where the output, notice, is taken on the right. So you'll note that the path from input to output through this amplifier goes through only 2 LC stages, whereas that from the input to output through that amplifier goes through 4 LC stages and 6 LC stages on the right. So each of these amplifiers carries a signal with a different delay from the input to the output, and therefore you've got a 3-tap filter where the tap spacing is determined by 2 LC sections, one on the input line and one on the output line. You've now realized distributed capacitance on both the input and output nodes and can realize a relatively high bandwidth with a structure like this. You may note a similarity between this structure, which was referred to in the original paper as an active transversal filter, but has also sometimes been referred to as a traveling wave filter. You may notice some similarities between this architecture and that of a distributed amplifier. But you'd note that on a distributed amplifier, the output would be taken on the right here, so that all paths through the network experience the same number of LC segment delays. Whereas here, by taking the output on the left, each tap amplifier carries a signal with a different delay to the output. And you'll note that with a traveling wave filter like this, the fundamental delay bandwidth product of the delay stages arises again. The tap spacing is proportional to root LC, whereas the delay line bandwidth is proportional to 1 over root LC, or inversely proportional to the tap spacing, dt. Also, you'll note that these structures are often used when technology is being pushed to its limits, so the maximum gain per tap is limited by the value of capacitances that arise in the ladders, because most of that capacitance is actually parasitic capacitance from the amplifiers here. Finally, I'd want to point out here that although there's obviously some active circuitry in the tap gains, P1, P2, P3 here, I still consider this a passive delay circuit because the delay itself is being completely provided by the passive LC networks at the input and output. These are just amplifiers providing some controllable gain in between, but the delay stages themselves are passive here. So to give you a feel for some of the numbers here, let's consider the case where you want to realize a 3-tap traveling wave filter. You then need a 3-section lumped LC delay line as shown here. If we want 25 picoseconds of tap spacing, then each LC segment has to provide half of that, or 12.5 picoseconds tap spacing, because the taps are separated by 2 LC delay sections, one on the input side, one on the output side. So that means the total delay time of each line is 3 times 12.5 picoseconds, or about 37.5 picoseconds, as shown here. So we see a group delay that's constant up to maybe 15 or 20 gigahertz here. Magnitude response also constant up to around 20 gigahertz here for our 25 picosecond tap spacing. And that's really marginal for a system that's processing broadband communication signals at 40 gigabaud per second. Now we can always extend that bandwidth by chopping up the capacitances by half, introducing twice as many inductors as before, but with half the value. And in doing so, we end up increasing the delay line bandwidth because we've got smaller values of L's and C's. But we've also reduced the tap spacing. So essentially we've got now a 6-tap filter with half the tap spacing, but twice the bandwidth. Well, you might say that, well, that's perfectly fine. If I really want 25 picosecond tap spacing, I can just turn off every other amplifier here and I end up with a 3-tap FIR filter just like I had before. The problem again is that the capacitances are primarily the parasitic capacitances associated with these amplifiers. So if I'm cutting these capacitances in half, the only way I can do that is if I cut the size of these amplifiers in half and therefore cut their transconductance or gain in half. So if I want to do that, I'm going to lose gain, or else I'm going to end up with a very different FIR filter, one with twice as many taps and half the tap spacing. But at least you can see here that doing so does have the expected result. We've got twice as many sections in the delay line, but each has half the delay, so we've still got our 37.5 picosecond total delay along the delay line, but we've doubled the bandwidth up to about 35-40 gigahertz. We've doubled the bandwidth over the magnitude response, over which the magnitude response is approximately constant. Now, some research we did in our lab at the University of Toronto about 20 years ago now showed that you could alleviate this delay gain bandwidth trade-off by a factor of 2 using what we call the crossover traveling wave filter architecture. The key recognition here was that we could take tap amplifiers in pairs, and crisscross their outputs as shown here. Now if you follow the signal flow through tap 2, for example, you'll see that the path through this amplifier experiences 5 LC sections of delay, and so does the path through that amplifier. So the gain of these two tap amplifiers will add up in phase at the output, so their gains sum together, and they really work together as a single tap with the same delay. The same is true for these two amplifiers serving as tap 1, and these two amplifiers serving as tap 2. So with this trick, we get back the factor of 2 in gain that we lost, and we can have our higher bandwidth LC delay lines in the input and output node. So we've effectively doubled the bandwidth of the traveling wave filter that we originally started with while keeping the same tap gain. So in summary, this architecture realizes a 3-tap FIR filter with the same tap spacing as we showed originally, 2 times root LC, but with twice the bandwidth that we achieved with that original architecture because we've half the size of the inductors and capacitors. So you'll see we've increased the delay bandwidth product by a factor of 2 here. We did demonstrate this architecture with a prototype implementation in 90 nanometer CMOS, which was at the time quite state-of-the-art. This was 20 years ago. It was a fully differential implementation, so the delay lines, although I've been showing single-ended delay lines until now, in fact they were realized with differential inductor structures and differential tap amplifiers, and that allowed us to save some area. Here's a die photo. You can clearly see the input coming in from the bottom. There's a buffer preamplifier that drives the delay line, and then the input delay line is on the bottom here. You see the differential coils that are stacked on top of each other to save area, and in fact their mutual inductance helps to increase the delay achieved per unit area. The tap amplifiers are in the middle. You note that they appear in pairs, and if you look closely you can even see their outputs crisscrossing as they're connected to the output transmission line, which directly drives the 50 ohm loads off chip. The capacitances here were about 125 femtofarads per side. These were dominated by the amplifier parasitics, again remembering that this was 90 nanometer CMOS. But about 1/3 of those capacitances on the delay line was provided by digitally controlled switched MIM capacitors. That gave us just the fine-tuning ability to adjust the LC products and ensure good impedance matching and fine-tune the delay along the delay line. This design was described in a presentation at the VLSI Circuit Symposium in 2005. Here are some measured results from the prototype traveling wave filter. Shown on the top left is the phase response through each of the taps measured one at a time. You'll notice that it's approximately linear. Again, the frequency axis here is shown on a linear scale to highlight the linear phase response, but there were some blips in the phase response. These can be due to imperfect matching along the delay line, certainly. Another thing you'll note with sinusoidal responses plotted here in the bottom left for each tap is that the inputs experience some frequency dependent delay as it travels from tap 1 to tap 2 and tap 3. And in fact, there can be some ripples in the magnitude response. You'll see that there's actually less gain through tap 2 here than there was through tap 3. So the bottom line is it is difficult to maintain a perfectly linear phase response and constant magnitude response with circuits like this, but fortunately in this application it's part of an adaptive filter anyway. So by adjusting the tap weights, the amplifier gains in the filter structure, you can somewhat compensate for these non-idealities in the delay sections themselves. In the follow-up paper in Journal Solid State Circuits for this work, you see here some eye diagrams demonstrating some equalization at 24 gigabits per second. Again, at the time in 90 nanometer CMOS, that was quite high speed. So we were then interested in looking at whether delay circuits and circuit architectures like this could be used for other types of analog signal processing that would be useful. And we knew that FIR filters are great, but they are limited in the types of frequency responses they can provide. You can get a richer collection of frequency responses if you allow yourself an IIR filter where you can also adjust the locations of poles as well as the locations of zeros as you can with an FIR filter. Specifically, if you're using a circuit like this for equalization in a wireline link, an IIR response has the potential to allow you to cancel some of the long tail on the pulse responses that arises in wireline links due to, for example, skin effect losses. So we focused on the IIR portion of the response in this next work because the FIR portion had already been described with traveling wave filters. And we realized that you can use distributed circuit techniques and LC ladder delay lines to realize a structure like that. Using an architecture like this, here the input comes into the delay line on the bottom left and feeds into the output delay line here, but then some amplifiers feed the output signal back to the input transmission line. One here with a gain of A1, one here with a gain of A2. And this then realizes some peaking in the frequency response related to the delay times around these loops. The amount of peaking could be controlled by the tap amplifier gains A1. So that was the architecture that we were interested in pursuing. A drawback is that, the peaking frequencies using a straightforward direct form IIR architecture as shown here on the left have to be separated by a factor of 2. The first peaking frequency is going to be at around 1 over tau, whereas the second peaking frequency is going to be at around 1 over 2 tau. And we knew that it would be more useful for equalization if we could locate the peaking frequencies closer together than that. So we adjusted the direct form architecture as shown here to provide the feed-forward amplifier in the middle, and then we could have 2 different resonant loops, one on the right and one on the left, with slightly different LC delay time constants, tau1 on the left and tau2 on the right. This gave us the freedom to locate the peaking frequencies independently for each side of this architecture. And we called this double loop multi-delay IIR architecture, and it allowed us to place the peaks of the magnitude response in closer proximity to each other and thereby realize more useful equalizer responses. So here's the fully differential prototype implementation that we developed. You can see the red delay line sections are labeled L1 and C1, whereas the blue delay line sections are labeled L2 and C2. So these indeed had different values, and thereby we realized different delays for each section, which are, of course, related to root LC. But in order to maintain a consistent characteristic impedance and good matching along this artificial transmission line that is required to maintain relatively constant delay over a bandwidth of interest, we had to ensure that this characteristic impedance, the ratio L over C, had to stay constant. So we could increase L, but when we did so, we had to decrease C. So here's a die photo of the prototype implementation. In this case, the differential input comes in on the left. Preamplifier drives the input delay line at the bottom. The center buffer feeds the signal to the output delay line at the top. And then we've got 2 feedback paths on the left and right, one providing low frequency peaking, one providing high frequency peaking. And the ultimate output appears over here on the right side of the die. This prototype was implemented again in 90 nanometer CMOS and was reported in electronics letters back in 2009. And here we see some measurement results. First, just showing magnitude responses deactivating tap 2 and activating only tap 1. So we're highlighting the peaking that results from the resonance around this feedback path. And you'll see that gave rise to some peaking at around 18 or so gigahertz, and the amount of peaking was programmable by adjusting the gain through tap 1. By adjusting the gain through tap 2, we could realize a programmable amount of peaking at a frequency of around 26 gigahertz. Now, combining these two, we could get a kind of a mixed peaking. So if we combine this peaking setting for the high frequency path with this peaking setting for the low frequency path, we can get a kind of a mixed peaking here at around 19 gigahertz that may be useful, more useful in some applications. Unfortunately, it turned out that for wireline applications, you really need some amount of boosting at these lower mid frequency range in order to serve as a good equalizer. So it's our expectation that the combination of an FIR filter together with an IIR filter like this might give you the extra flexibility that's needed to shape the frequency response as needed for any particular wireline channel. At the same time, perhaps it would have been better to shift those peaking frequencies lower into this range and move them together down there to give us more low frequency boost for skin effect losses. We've so far focused on the use of ladder filters as passive delay circuits, but it's also possible to use lattice structures, such as the one shown here, to realize passive delays. And lattice filters do have some interesting properties that make them useful for this. So specifically, if we've got a lattice section like this, where Z1 and Z2 are passive impedances, it turns out that as long as Z1 and Z2 are chosen to satisfy this criteria here, that is their product equals the terminating resistance R0 squared, then it's got a couple of useful properties. First of all, it's got an all-pass response of the form shown here. That's useful for providing a constant delay, as we know, because it ensures a constant magnitude response across all frequencies and provides left half plane poles and right half plane zeros, contributing extra phase shift. And it's also the case that if this criteria is satisfied, the input impedance looking into the LC ladder section is precisely equal to the terminating impedance. So it's like it just kind of reflects this terminating impedance precisely at its input port. As a result of that, we can cascade lattice stages like this indefinitely without changing their response at all. The lattice stages, in fact, can each be different. As long as each one satisfies this criteria, they can be cascaded. And we can really, as a result, provide more delay for a given filter order than we can with an LC ladder. Now, LC ladders are still useful because all their impedances, the capacitive impedances are grounded in an LC ladder. And so that is the case for parasitic capacitances. So that makes them kind of natural for distributing parasitic capacitances. But whereas lattice filters have these crossing impedances. Having said that, for some applications, lattice filters can be a more efficient way to realize a larger delay. Just to give you a feel for what these can look like, you can have a first order lattice section such as the one shown here. Each section affords an all-pass response, and we just have to make sure that the inductance and capacitance values are chosen to satisfy this criteria here. On the other hand, if we want a higher order lattice section, we need parallel combinations of L and C, as well as series combinations of L and C in these crossover branches. Doing so allows us to have complex conjugate pole zero pairs and gives us more flexibility in determining the frequency response to the lattice section. But remember, in both cases with appropriately chosen passive component values, the input impedance is simply equal to the impedance looking into the terminating resistor. So we can actually mix and match these stages as we like to realize higher order delay functions without altering their response. So for example, we can get a third order delay response by cascading first order section and a second order section. So to give you a further feeling for what these might look like in practice, here are examples of lattice delay sections designed for about 80 picoseconds delay. First order section here has 6 nanohenry inductors with crossing 266 femtofarad capacitors, and then again down here we've got more inductors for the crossover path as well. So the area will start to get larger, obviously, but we're realizing here about 80 picoseconds delay in both cases. Now, although the ideal delay lattice sections are shown on the left, if we realize these inductors on an integrated circuit, there's unfortunately going to be parasitics associated with them. And here are exemplar values, typical values that would arise for inductors of 2 and 6 nanohenries respectively. And so you see some capacitances to ground as well as some series resistance. Both of those are going to cause the response of these lattice sections to deviate from their ideal value. And so here are some simulation results illustrating that. You can see the magnitude response is not quite all pass at 0.5 volts per volt, which would be just the straight voltage divider between source and load resistance here. The first order section has this low pass response to the solid line. The second order response is the one shown here. And just for comparison, here's an ideal second order all pass Bessel response. The group delay response is plotted here on the bottom. So again, a second order Bessel response would be constant at around 80 picoseconds up to 4 gigahertz with these component values, but introducing the inductor parasitics for integrated circuit inductors lowers the bandwidth over which constant group delay can be maintained down to about 3 gigahertz. But again, this could still prove useful for some analog signal processing with this delay of 80 picoseconds up to about 3 gigahertz. For example, if you're interested in realizing a 3-tap FAR filter with a tap spacing of 80 picoseconds, you could use the second order lattice sections shown on the last slide. They were designed to approximate a second order Bessel response, deviated from that because of the inductor parasitics, of course, but you'd end up with a passive circuit like this with 8 inductors and with a total estimated area in this case of about 0.1 millimeters squared for this delay line. So you can decide for yourself whether that might be attractive for some particular application. We were interested in structures like this, not to realize an FAR filter, but to actually implement analog continuous time pipelining. So shown here on the left is a traditional discrete time pipeline analog digital converter. In such cases, the analog pipelining is performed by discrete time delays realized by switch capacitor circuits, usually with an amplifier in feedback. And so, as you know, on pipeline A to D, each stage does partial conversion of the analog waveform to digital and then passes a residue on to the next stage. Now, prior work showed that instead of using a discrete time delay, we could replace that with a continuous time delay, such as we've been talking about. Here, the ideal delay is shown, but instead we're going to approximate that ideal delay with some passive circuits. There was alternative work cited here in the top right that was actually interestingly approximating a negative continuous time delay in the other path to try to perform the same function. So in this application, an analog waveform coming in on the left here is being quantized and held by the DAC here in order to be subtracted from a delayed version of itself, forming the residue signal here, epsilon. So for good performance, what we require is the response through this continuous time delay path G to match the delay through the quantization path. So you might say that we just wanted to provide an ideal continuous time delay with the delay time equal to the clock period through this quantization path here. And prior work had sought to do so with lattice circuit here. But we recognize that through this path, the frequency response is not just providing a constant delay, but the zero order hold associated with the delay converter output is also performing some shaping of the magnitude responses, subtly low pass filtering the frequency response through here with a sine f over f shape. So if we really want the best performance here, we want the delay through G to have not just a relatively constant group delay, but to also have this sine f over f magnitude response. So the transfer function G was therefore cast into a rational, generalized rational form as shown here, and an optimization performed to find the rational transfer function coefficients for G that would minimize as a cost function the difference between the frequency response through G and that through this quantization path, which we call T. Minimizing the mean squared difference between those two frequency responses over our bandwidth of interest would result in the best possible G for a given order n. What we found was that by doing so, we could actually achieve good matching between the continuous time delay path and the quantization path over a wider bandwidth using a much lower filter order. So the prior work shown here in blue is actually a fourth order response, but we found that a second order response plotted here in black could provide just as good matching. This is the error function plotted here on the y-axis versus frequency, and so you see the error remains even lower than the fourth order response over the bandwidth of interest, despite the fact that only a second order response is being used here. Again, lower response is important because the size of those inductors is significant, so that allows us to have a smaller delay line. And so here are some of the details of the implementation. Again, since we're not realizing a perfectly constant magnitude response, the LC lattice network had to be modified to introduce some resistors into it, and the resulting optimization gets quite complex. We can't, in fact, precisely realize the desired frequency response shown in black, but we can closely approximate it, resulting in the error shown here in red. Again, it's still less error than was observed for the higher order previously reported lattice filter shown in blue. So in this next part of the presentation, we'll turn our attention to passive delay circuits realized out of transmission lines integrated on die. These don't have the bandwidth limitations associated with LC networks, but they can consume even larger area than LC ladder networks. The idea here is simple and is illustrated in this example with a 2-tap FIR filter. The idea is simply to realize the delay element with a suitably chosen length of integrated on-die transmission line. And then take the input and output of the transmission line, form a weighted sum of them across a load, and that's the output of your filter. Now the transmission line has to be terminated so that the input traveling along it doesn't experience any reflections. This is a little cartoon of what it really looks like. The input is introduced to one end of the transmission line, and rather than just have a long strip proceeding for a few millimeters across the chip, we can fold the transmission line back on itself. This helps co-locate the 2 tap amplifiers so that it's easier to form their sum at a common point. Here's an example design that was done in our lab many years ago of this 2-tap transversal equalizer. Now you'll notice that the transmission line that provides most of the delay is pictured here and is 3 millimeters long physically, but it's folded back on itself as illustrated on the last slide to make it a little more area efficient. the tap outputs are summed together. The input through this common source transistor M1 serving as a transconductor, and the output of the transmission line goes through two common source transconductors M2 and M3. That provides a sign inversion so that the FIR filter tap weights have opposing signs. That allows us to provide a boost at high frequencies relative to low frequencies. The two transconductor tap outputs are summed up on a 50 ohm load in the current domain. The red highlighted inductors are used to improve the equalizer's input and output matching. Otherwise, you'd see some discontinuity associated with the parasitic gate capacitances of M1 and M2. But notice that these inductor values are very, very small. Those are the values required to help nullify the parasitic capacitances associated with the transistor. So rather than introduce spirals, all that was required for these values of inductance were narrow strips of metal with suitably chosen dimensions. These provide 73 picohenries of inductance each. Here's a die photo of the design. We presented it originally at the RFIC Symposium in 2008. It's an old 0.13 micron CMOS process. And you'll see the input comes in here and proceeds along the long transmission line here. The tap amplifiers are co-located here along with the 50 ohm load, and then finally goes off chip. And so here are some eye diagrams measured at 38 gigabits per second. It's obviously a fairly high speed in that very old technology. We passed a 2PAM waveform through a channel response exhibiting about 14 dB of loss at 1/2 the baud rate, 19 gigahertz in this case. And you see that the input to the equalizer has a relatively closed eye diagram, but that by the time it reaches the output, we've got a little bit of eye opening observed. So we've so far looked at the motivation and background for our interest in analog, continuous time, broadband, integrated delay circuits. We looked at some applications that were of interest: pipelining analog signal processing, FIR filtering, time interleaving, and we looked at their implementation using passive-only elements. And we saw that one of the main drawbacks with the passive elements is the fact that they use relatively large components, especially the inductors and/or transmission lines. Now, technology trends, fortunately, are affording us better and better metallization in the high layers of the interconnect. These have lower and lower series resistance, lower losses associated with them. At the same time, as applications proceed to higher frequencies, we're more and more interested in relatively short time delays, which allow passive delay lines to become more compact. So these trends tend to favor passive delay lines. However, they're still relatively large, and for some applications, all that on-die area is just going to be intolerable. So for that reason, we're going to now take a look at active implementations of analog continuous time broadband delay circuits, which we'll see can have smaller implementation area.